Outside that, no, I had a better idea. That was a joke.
All right, let's get started because we have a lot of things to do today. First of all, another day, another T-shirt. I don't know, I didn't like this one particularly, but you decide yourself. It's too big, baggy, and bland, but I don't know, whatever you guys sent me. You looked at me and you assumed that I need this gigantic one. All right, so the topic for today is extra dimensions, and we'll start from the very beginning, and it looks at the moment that it's an orthogonal topic compared to what we discussed about pseudo-Goldstone-Higgs and collective breaking, but I'm really hopeful that by the end of this lecture you will understand that most of the really interesting ideas that are related to extra dimensions are actually just a rephrasing of the same collective breaking pseudo-Goldstone boson Higgs ideas, composite Higgs ideas that we were discussing in the first three lectures. Okay, so let's get right into it. So we assume for now that we have one extra spatial dimension, just to get started. And of course, the first thing that we have to ask is, well, since we haven't seen that extra dimension, yes, that extra dimension cannot be, at least for now, cannot be an infinitely large extra dimension. It has to be a compact dimension. So we are going to be assuming that we have an extra circle that has a radius r. And we'll be trying to ask the question, if I look at the field theory on this 5-dimensional theory compactified in a circle, what will a 4-dimensional observer see? Yeah, so this will be the story of the Kk decomposition and Kk towers. Yes. So let's take, just a scalar field in this 5-dimensional theory. You write down the Lagrangian d phi x, dm phi, dm phi, where now this m, yes, is the index that goes over the normal 4 dimensions plus the additional 5th dimension. So it's usually denoted as 0, 1, 2, 3, and then 5. That's the way people usually write it. They don't put 4, but and x5, the 5th component, we are going to denote as y. Yes. And then the question is, so what will a 4-dimensional observer see? Yes, somebody who cannot resolve the size of this extra dimension. Yes, what will be the effective theory from the 4-dimensional point of view? Well, okay, so you rewrite this in terms of the 4-dimensional derivatives d mu phi squared minus dy phi squared 1/2. Yes. And here we were assuming that we have a circle, so you have a periodic function, yes, because you have a circle, so you can do a Fourier series along the y-coordinate. Yes, so you can write your full field, without losing any generality. Yes, you can write it as a Fourier series phi n of x. Yes, so this will be this phi n of x. You can think of that as the Fourier expansion coefficient of the different modes that are winding around the extra dimension. Yes, except of course now it's still a function of the 4-dimensional coordinates. Yes, times e to the I n over r times y. Okay, and so the sum goes from -infinity to +infinity, and in order to get normalizations later on right, I will put here 1 over root 2 pi r factor. You will realize later on what the significance of that factor is. It's basically going to connect the 5-dimensional and the 4-dimensional field, which will have different dimensions. Yes? It doesn't have to be. It's just a very simplest example that I can sort of, show you some of the basic properties of what happens when you are looking at a compact extra dimension. Yes, it doesn't have to be. It could be on an interval. It could doesn't have to be a flat space. Yes, we'll be discussing all of those possibilities later on. If it's more than one dimension, could be on a torus, could be complicated manifolds. It's just, the simplest thing that you can think of that is not ridiculous. Yes. Okay. Very good. So then you go ahead, shove this Fourier series into the action, and just perform the integral over the extra dimension. Yes. So from the 4-dimensional point of view, you will get d4x some n is greater than 0 here, d mu phi n star d mu phi n. Yes. So you will get the normal kinetic term for a 4-dimensional field, but now, of course, it's a sum over an infinite tower. So all of these Fourier expansion coefficients will become independent 4-dimensional fields. And the dy term, yes, so this is a term that is telling you how many times the particle has been winding around the extra dimension. Yes, so that is corresponding to a momentum along the extra dimension. Yes. So that, from the 4-dimensional point of view, will show up as a mass term for these different 4-dimensional fields. So you will get here minus n squared over r squared phi n absolute value squared. Okay. So here is the first and most important statement. Probably everybody knows it, but it's good to get everybody on the same playing field. When you take a higher dimensional field, from the 4-dimensional point of view, it will look like an infinite tower of field. So this is usually called the Kaluza-Klein decomposition. So this is called the Kk decomposition. Yes, and these. What happens to the zero mode? Well, the zero mode will just have zero mass. Oh, probably it's greater or equal. Yes. Yeah, so there could be a zero mode, yes, and that will just have zero mass. Very good. So a 5-dimensional field from a 4-dimensional point of view will look like a tower of fields with increasing mass. Yes, so the momentum along the 5th direction will show up as a mass term from this effective 4-dimensional point of view. And if you have more than one extra dimension, there will be similar formulae. Yes. So if you have 6, 7, 8, whatever dimensions you have, the expression for the masses will be, there will be an integer telling you how many times it's winding along the 5th direction, the 6th direction. Of course, again, this is assuming you have a simple torus-like geometry. Yeah, so there will be an m0 squared. So here I didn't add a bulk mass, but you could have added a bulk mass for the field as well. So there will be a bulk mass term that you add, and then plus these r5 squared plus n6 squared over r6 squared plus etc. Okay, so this is what you're going to get. So this is how you do a Kaluza-Klein decomposition. Okay, so that's for a scalar. Okay, so now what happens if you have a gauge field? Yes, so for a gauge field, there will be slightly more complications. Yes, so let's say I take a gauge field. Yes, a mu. Yes, but the important thing is that now when I take a gauge field in the extra dimension, yes, there will be more variables here, x, y, but also the index of the gauge field, yes, am, is now going to run over more possibilities. Yes, because the gauge field in 5 dimensions will have 5 components. Yes, of course, you still have to worry about gauge invariance, remove all the gauge redundancies, etc., and make sure how many actual propagating degrees of freedom there are. But anyway, just nominally, there is an extra component here. Yes, so you do the same thing. You play the same game. Yes, 1 over root 2 pi r, yes, times sum over n, am n of x e to the I n over r times y. Yes, but again, there's another type of decomposition that you have to do here, yes, which is to take the am and decompose it into a 4-dimensional gauge field and into an a5 which would be a 4-dimensional scalar. Yes. So there is one Kk decomposition saying that, well, there's an extra coordinate, and then there's an extra component here. Yes. So you can think of this. You have your gauge field. Yes. You have your A0, A1, A2, A3. Yes. And then there's the A5. Yes. And then these guys here will naturally form something that is a 4-dimensional gauge field. There will be a tower for them. Yes. One component will be massless, and then the rest is massive. And then there's this additional scalar. Okay, so you go ahead, shove this now into the action of a 5-dimensional gauge theory. Yes. So integral d for x dy minus 1/4 fmn. Okay, so that would be the action for just take the Maxwell action from 4 dimensions and lift it to 5 dimensions. Yes, and then you rewrite it as a decomposition both in terms of these Kk modes. Yes, and the decomposition also in terms of the components. Yes, so I'm not going to go through every step. I will just give you the answer. Yes, so there will be integral d for x, and then there is the usual 4D Maxwell action minus n f mu nu n. Yes, so this is the 4D Maxwell action for the 4D parts of the gauge fields. Yes, and then there is going to be sort of a strange piece here. Yes, which is d mu a minus n times minus d5 a minus n. Yes, times dn a5 d mu a5n minus d5 a. Yes. So basically what you get is, and then there will also be the mass terms that I didn't write down, plus mass terms. Yes. The important thing that I want to emphasize is that you get this strange term here, yes, that is actually going to mix the A5 and the A mu components with each other. Okay? So actually, yeah, this is really not, I haven't really performed it. Anyway, this piece here still has d5 derivatives. Yeah, there's a sum. Yeah, I'll write it bigger next time. The upshot is that there's a mixing between A mu and A5. Yes. And the question is, what does that mean? Yes, and should we be shocked about that? Yes, what is the physics behind it? Yes. Well, the physics is that you will get a Kk tower for gauge fields. Yes. And you know that a massive gauge field has a different number of degrees of freedom than a massless gauge field. Yes. So I guess I shouldn't write here. In 4 dimensions, a massless gauge field has 2 propagating degrees of freedom, yes, 2 transverse degrees of freedom, as you know from Maxwell's equations. Yes, but a massive gauge field, yes, like the W and the Z, has 3 degrees of freedom. Yes. And what we know is, what has to happen is that there's got to be a Goldstone boson, yes, that is being absorbed. A scalar has to be eaten by the gauge field in order to make it massive. Okay. So now what is happening here in the 5-dimensional theory is actually exactly that. And that's what that mixing term is signifying for you. Yes. There will be a mixing term between the A mu and the A5, yes, as long as n is not equal to 0. Yes. And what you are actually finding is that there will be a massive tower for the gauge fields. Yes. So there will be an A mu n when n is greater than 0 is a tower of massive gauge fields, massive spin 1 fields. yes, which actually corresponds to 3 degrees of freedom, yes, and that will actually eat the tower of the A5 scalar fields. The fields that would appear as scalars from the 4-dimensional point of view will actually be absorbed by the A mu, okay, except the 0 mode, yes, because at the n equals 0 level, yes, the 4-dimensional gauge field does remain massless, yes, so it actually has only 2 degrees of freedom, yes, so there's nothing that needs to be eaten there. So the 0 mode of the A5 will remain a physical mode. Okay, so we will get an A mu massless for the gauge field plus an A5 massless scalar. Okay, so what I want to emphasize is that once you get to the Kk decomposition to more complicated fields, yes, there are more subtle things happening. It's not super complicated. If you think the physics through, then you can understand it relatively easily, yes. But what you do find, for example, for the gauge field is you get a tower of massive spin-1 fields plus a single, no tower, yes, massless scalar field. Okay, and you can understand it well from the point of view of the counting of degrees of freedom. Okay, and I wrote it down in the notes. You can actually just go to a particular gauge and remove all the n not equal 0 A5s. Yes, that will actually remove the mixing that we have found there, and you will truly find the action that you are expecting. Okay, so if you had an even higher dimensional gauge theory, yes, so let's say you have a 4 plus n dimensional gauge theory. Yes, so what you will find then in that case, yes, so you will have a gauge field that has 4 components here, yes, and then something that would look like n different scalars from the 4-dimensional point of view. Yes, so you would have here A mu, you would have A5, A6, A4 plus n. Yes, and what will happen is that one combination of these scalars from the 4-dimensional point of view will be eaten. Yes, so you will find a single massive Kk tower for the gauge fields. Yes, so the Kk decomposition will be one massive spin-1 tower. Yes. Then n minus 1 massive spin-0 towers. And then, of course, at the 0 mode level, you will just get a massless 4-dimensional gauge field and n scalars. Okay, very good. How about gravity? Okay, so you'll have to play the same game for gravity, for the graviton. Yes, so you have here your higher dimensional 4 plus n dimensional metric. Yes. It's a symmetric matrix. So here you have your G mu nu. From the 4-dimensional point of view, there will be n vectors. Yes. All of these are going to have one 4-dimensional index. Yes. And then the other index is going to run along the extra dimension. Yes. So it will look like, from the 4-dimensional point of view, n vectors. Yes. And then here, there will be a bunch of scalars. Okay? And, of course, at the massless level, that's exactly what you're going to get. And so at the massless level, you will get a 4D massless graviton. Yes. You will get n massless gauge fields. And then you get here this n times n plus 1 over 2 scalars. Okay, at the massless level. Now at the massive level, it will be more complicated. Yes, because the four-dimensional graviton has at the massive level has 5 degrees of freedom, and at the massless level has 2 degrees of freedom. Yes. Graviton in 4D at the m equals 0 level has 2 degrees of freedom, and the massive level has 5 degrees of freedom. Yes. It's a helicity 2 state. Yes, so it will have the 2, 1, 0, -1, -2 state, while at the massless level, as we know, massless particles, have basically just one helicity, so 2 and -2. Yes, so this guy has to eat one gauge field, one massless gauge field, and one massless scalar. Yes, so this 5 degrees of freedom eats one a mu plus one scalar. Yeah, so there are only n-1 gauge fields, gauge towers that are left over. Yes, one tower of the a mu's is going to be eaten. So there are n-1 massive towers, massive a mu tower left over. Yes, but in order to make this one massive, yes, each of those has to still eat one scalar. Yes, so one scalar will be eaten here. Yes, and then n-1 scalars will be eaten there. Yes, so in total, n scalars out of the n times n plus 1 over 2 will be eaten. Yes.
So,
Right.
In the case of vector, the scalars that are eaten has interpretation in terms of 2D both from both.
Right. Exactly.
Here for the gauge field, do we have that similar interpretation in terms of there is some where
Probably. Yeah. Yes. Probably. Yeah. All right.
the gauge group would be always U1 in this case?
Right. Yes. Well, sorry. So there's no. So this is just a massive tower of gauge fields. Yes. So it's a massive tower. Yes, so. Right. Right. Yeah. So I guess. There are n massless gauge fields. Yes. Yeah, but I guess it should be thought of as U1. Yes. So it depends on the geometry of the extra dimension. Yes. So that corresponds to what kind of geometry of the extra dimension has. Yes. If it's just a bunch of, if it's a circle, it's a U1. Yes. If it's tori, it's going to be products of U1s. Yes. If it's a more complicated manifold, yes, then you can get a non-abelian gauge symmetry there. Okay. So, but that's something that I don't really know a whole lot about the non-abelian part here.
Okay.
Yes.
So when you say massless and massive, it's just the zeros tower and
Right. It's just the n equals 0. Yes.
Okay.
That's not a tower. It's just that one mode where n equals 0. Yes. And all right. Very good. Now the matching of the couplings. Okay. So we understand how to take the fields, how to decompose them. Now how to match the couplings. Yes. Well, first of all, you have to notice that the dimensions of the fields in a higher dimension and in in 4 dimensions is different. Yes. So if you just do true dimension analysis for the fields, yes, what you find is that, well, of course, the action is always dimensionless. Yes, that's the basic tool for dimension analysis. And then let's say a scalar field in extra dimensions, 4 plus n dimensions, yes, will still look like the kinetic term. The way I wrote it, yes, it's just the derivative phi squared, yes. But this will tell you that this 5-dimensional field has a different dimension, yes, because now you have a higher dimensional integral here, yes. So what you get is that 2 plus the dimension of phi times 2, yes, and then here minus 4 plus n should be 0, yes. So from that you find that the dimension of a scalar field in a higher dimension, yes, is 1 plus n over 2. Yes. So for example, if you have one extra dimension, the dimension of the scalar field will be 3/2 instead of 1. Yes. Now, same thing for fermions. Yes. So in this case, you just write the Dirac action. Yes. So it will have one derivative instead of two derivatives. So you just have one less here. So what you find is that the dimension of the fermion in a higher dimension is 3/2 plus n over 2. Yes? So in 4 dimensions it's 3/2. Yes? In 5 dimensions it's going to be 2, etc. Very good. So now how about the covariant derivative? Yeah? So d mu is usually d mu minus I g5. Let's say, let me write it as dm minus. Yeah, so this is how a covariant derivative will look like. Yes. Now this derivative is dimension 1. Yes. But now this gauge field, yes, actually a boson will always have the same dimension as the scalar, so it will not have dimension 1. Yes. It will have dimension 3/2. Yes. So that means that the 5-dimensional gauge coupling actually will have to have a dimension. Yes. So the 5D gauge coupling will have dimensions. And that's, of course, not shocking. Yes, you have heard about the fact that 5-dimensional gauge theories are not renormalizable. So they will have a built-in cutoff from the fact that your coupling is actually a dimensionful parameter. Okay. Now, when I plug in the Kk decomposition there, yes, for the gauge field, yes, what I can write here is, for example, for the 0 mode, I can write a mu 0, the 4-dimensional version, times 1 over root 2 pi r. Yes. And then this has to be multiplied by g5. Yes. And this is what is then eventually going to give rise to what the 4-dimensional effective gauge coupling of the theory is. Yes. So g5 over root 2 pi r, yes, should be identified with g4. Yes, and this makes perfect sense. This is dimensionless. Yes, this guy here, yes, has to have dimension minus 1/2. Yes, because this has dimension 3/2. Yes, this has dimension 1. Yes, so the 5-dimensional gauge coupling has to have dimension minus 1/2. Yes, so this is how you are going to match in the simplest example the higher dimensional and the lower dimensional couplings to each other. Okay. Now, in general, the expectation is, at least in the case when there are no complicated background curvatures, which we will get to in a moment. Yes, in general, what you are going to expect is that your 4-dimensional gauge coupling squared is going to be given by the higher dimensional gauge coupling squared divided by the volume of the extra dimension. Okay, it's very simple. You can see it in many ways. You can see it like that. You can see it by going. The other easy way to see it is by going to sort of the non-canonically normalized version of the theory, of the gauge theory, where you have a 1 over g, let's say 4 plus n squared f mn squared in the action, and then just perform here d4x dny. Yes, just perform through literally the integral over the extra dimension, and you'll see that it's the volume that is going to show up here divided by this g4 plus n squared. That's what needs to be identified with 1 over g4 squared. Okay, so that's the matching for the gauge coupling. How about the gravitational coupling? Okay. The matching of the gravitational coupling, well, that's slightly different, yes, because already the 4-dimensional gravitational coupling, which is the Planck scale, is dimension full. Yes. So the 4-dimensional gravitational action is minus m Planck squared times integral root g times r, yes, d4x. Yeah, so what I'm supposed to do is I'm supposed to write the analog of the, the Einstein-Hilbert action for a higher dimensional gravitational theory, then shove in the gravity zero mode, yes, and then find out how that higher dimensional Planck scale is related to the four-dimensional Planck scale. Okay, so I'm going to write the analog of this for a higher dimension, yes. So in that case, yes, there will be an integral root g times r d4 plus n x, and this is the higher dimensional curvature. This is the higher dimensional metric. And then you see here you have more, the dimension of root g and r in higher dimension in fourth dimension is the same, yes, but you have more integrals here. Yes, so the higher dimensional Planck scale will show up at a different power in the gravitational action for 4 plus n dimensions. Yes, so the way it is written usually is, let me call this m star to the power 2 plus n. Okay, because you added n dimensions here, so you have to add another n dimensions over there. Okay, and then what you do is, again, you take your higher dimensional metric, decompose it along the lines that I have outlined over there, shove it into the four-dimensional action, and you find that, well, the matching of the four-dimensional and the higher dimensional Planck scales will be very simple. Yes, well, you have to take the higher dimensional Planck scale and multiply it by the volume of the extra dimension to get the four-dimensional Planck scale. Okay, so the most simplest matching is that m Planck squared equals this m star to the 2 plus n times the volume of the extra dimension. Okay, very good. So that's the matching. Again, it's assuming that the extra dimensions are flat. Okay, we'll get very soon to warped extra dimensions, and then this matching relation will be somewhat different. Okay, root g of the higher dimensional metric, root g of the 4 plus n dimensional metric, yes, and then so that's this bigger matrix that I have written somewhere here. Yes, you have to take the root g of this whole thing, yes, and then you have to see how this zero mode is contained in the bigger root g, yes, and you go through that, and then this simple result, the naive one, is exactly what you're going to get there. Okay, very good. So before branes were introduced, the assumption was that, well, if you have a natural theory, yes, then the energy scales are going to be set by pre-branes, so without introducing branes. That means that every field, every standard model field, everything that you observe propagates in every dimension. Yes, a natural theory should be such that everything is set by whatever the fundamental scale of the theory is. I'm going to call this m star. Yes, so in that case, the higher dimensional gauge coupling, yes, this is dimensionful, yes, should also be set by m star. Yes, so you would assume that this is going to be set by m star to the power minus n over 2. Yes, this is how, if you go through, what the dimension of the gauge coupling in a higher dimension is. Yes, well, it depends on the number of dimensions. And then what you know is that, well, so I will have to match this coupling, yes, down to the observed four-dimensional gauge coupling. Yes, I know how to match it. I have to match it with the size of the extra dimension. Yes, in order to get out of this dimensionful coupling something that is going to be order 1. Yes, it means that the volume of the extra dimension should also be set by this m star. Yes, so the volume of the extra dimension should be also set by m star. Yes. But then, if this is of the order of m star, yes, this is of the order of m star, Yes, that means that the radius of the extra dimension should be roughly set by 1 over m Planck. Okay, so that's pretty bad, yes, because it means that it's super, super tiny. Yes, so there's absolutely no hope for ever observing it. So the actual relation that you get here is that the size of the extra dimension should be of the order of 1 over m Planck times the 4-dimensional couplings to the power n plus 2 over n. Okay, so the extra dimensions are super tiny. It's just to remind you, of course, the m Planck is something of the order of 10 to the 19 GeV. So it means that the Kk modes that are propagating in something that is as small as 1 over m Planck, yes, the mass of the Kk modes is set by 1 over r. And so those would be Planck scale or roughly Planck size. There could be order 1 factors here, yes, but something that is super, super small and definitely not observable. Okay. Now, when branes are added, then the situation changes. So branes are lower dimensional objects, sometimes solitonic, sometimes fundamental, yes, that can trap fields on their surfaces. So these are lower dimensional objects. Okay, so the word comes from the analog of membranes. Yes. So these are lower dimensional objects that show up in string theory, but could also be sometimes showing up as solitons in ordinary field theories that trap fields on their surfaces. Yes. So in particular, if you have something that is called a 3-brane, yes, so that would be an object that has exactly the full dimensions that we are observing. Yes. And if you had a 3-brane that is trapping fields, yes, for example, it's trapping the gauge fields or the standard model fermions, yes, then you can imagine that you have a theory where the standard model fields are localized on a 3-brane, which is basically like the world that we are observing. Yes. And there are some extra dimensions where the standard model fields don't propagate, but, for example, only gravity propagates. 3, when you say a D brane, I mean an N brane, yes, it refers to the spatial dimension of the brane. Yes? So the 3-brane is a 3 plus 1, 3 spatial dimensions, and then, of course, there's time. Yes, so you can have, this would be a 3-brane. Yes, you have the standard model that is, here you have your electron-positron scattering. That's all stuck to the brane. Yes. However, gravity, of course, that's the fluctuation of space-time. That's something that you cannot, or at least not naively, the way we are thinking about it, you cannot localize it like this on a brane. Yes, we'll see that in warp space that's actually not true. But okay, so gravity, yes, goes into the extra dimension. The standard model is trapped on the 3-brane. Yes? So this leads us to the first topic, yes, which is the large extra dimensional scenario. So this is also called the ADD model, Arkani, Hamed, Dimopoulos, and Dwali. Okay, so again, the idea is the standard model is trapped on a 3-brane, and the strength of gravity is going to be diluted by the fact that there are large extra dimensions, yes, while the strength of the standard model interactions is not diluted because it's trapped on the brane. So the idea here is that is it possible that the fundamental interaction strengths of gravity, that m star that I have written there, is actually the same as roughly the weak scale, 1 TeV, yes, and that there is no hierarchy problem, yes, just because there is actually no different scales in the theory. Yes. There's only one scale in the theory that's the fundamental gravitational scale. And the only reason why we think that there is another very high scale in the theory, which is the Planck scale, is because the size of the extra dimensions is very large. Okay, so there's no hierarchy, or at least that's what the idea here is, because there is no high scale. So the fundamental scale of physics is actually a TeV, and it just appears to be much higher because gravity is going to be diluted by the fact that it has this large extra dimension available to it in which it can propagate, while the standard model, there you just feel the fundamental strengths directly because it's localized on the brane. Okay, well, so that's very nice. But then there is something, there is a particular prediction for how large the size of this extra dimension has to be, yes, because, still that matching of the couplings for gravity that I have written down over there has to be satisfied, yes, so that will tell you that the size of the extra dimension in this case should be given by 1 over m star times m Planck over m star to the power 2 over n. Okay, so you see that this would be 1 over TeV here, yes, so that would be what you would naturally expect, and then this factor is telling you how much larger does the extra dimension have to be compared to its natural size in order for us to actually observe the true m Planck, the 10 to the 19 GeV, as the effective coupling. Okay, so it depends on the size of the extra dimension. When n equals 1, the radius of the extra dimension has to be 10 to the 15 centimeters. Okay, well, that's probably not true, yes, because that's something of the size of the solar system, so we probably would have noticed that. But for n equals 2 already, what you find is that r is about 0.1 centimeter, so about a millimeter, and for n greater or equals 3, the radius of the extra dimension is already less than a micron. Okay. Well, you shove it in there, but I mean, what you will see is it will, when n is very large, yes, it will start approaching 1 over TeV. Yes. Okay. So this is excluded. Yes. Now this n equals 2, 1 millimeter. Yes. It turns out that actually that's just on the borderline of being excluded by tabletop gravitational experiments. So this is borderline excluded or borderline okay. But what does borderline excluded mean? It means that, well, if you take m exactly 1 TeV, yes, then the tabletop experiments, are just barely sensitive enough by now to exclude it. But okay, you take it then 2 TeV, yes, and actually, what I wrote here, I don't know whether that's still true. That m star has to be 1.4 TeV. Okay, yes. Well, yeah, so that can change a lot, yes. I mean, you can have cigar shapes, yes, some extra dimensions big, some extra dimension not so big. Yeah, you can play around with that. And people have done that for a while. Okay. I'm sorry? No, it will. So there are other tests outside of gravity. Yes, because, the one thing that I should emphasize is, yes, so now this R is very small. So for example, you take this, is a millimeter, yes? So that means that there will be particles, there will be Kk tower that is spaced by 10 to the minus 3 electron volt. Yes? It starts at 10 to the minus 3 electron volt. It will have a Kk tower that is very, very dense. Yes? Now why is that not ridiculously excluded? Yes? Because these guys are going to interact with 1 over m Planck. Yes? So the interaction strengths, so there will be a lot of these graviton particles, yes, but they are super weakly interacting. Okay, I don't have time to go through that, but actually what you can do is you can take into account the collective effect of these, each of them individually, of course, 1 over m Planck suppressed, yes, and then even the 10 to the minus 3 electron volt is heavy enough to put it outside of the bound of fifth force experiments. Yes? But they will still have a collective effect. And you can actually show that their collective effect will be something that is basically a 1 over m star induced effective operators. Okay, so actually the collective effect of these, very dense but very weakly interacting Kk modes will be as if there was a, 1 over TV suppressed operators. Cosmology, yeah. So you have to absolutely worry about it. That's a big problem. Yes, to make sure that we get the usual history of cosmology. I didn't remind myself how exactly it goes, but the reheat temperature cannot be very high. It should be very low. So there are many issues there. The one thing I want to emphasize is that actually, we say this is a solution of the hierarchy problem, but what it really is just a reformulation of the hierarchy problem. Yes, because if it was truly a natural theory, yes, with one scale, m star, yes, then R better be given by 1 over m star as well. Yes? So what you have here is, yes, you have a huge factor, yes, that is telling you that the radius is everything is given by m star, but for some reason the radius happens to be super large. Yes, in fact, for n equals 2, if you count this number, that's exactly 10 to the 16, 16 orders of magnitude. Yes. Now, if you go higher, yes, that you can distribute it. Yes, but basically, what you did is you reformulated the hierarchy problem of why these two scales are coexisting with each other to the question of why is the radius so much larger, yes, than the one scale in the theory. Okay. Nevertheless, it's a fun phenomenological model, and you can play around with it. I have written down several other observable effects that the presence of these Kk modes will have. Basically you will have missing energy events, yes, because these gravitons are going to be disappearing, yes. So you will have the usual, monophoton, monojet plus missing energy kind of events. You will have, it will actually affect supernova cooling, so that will give you one of the strongest bounds on this model because they will act like axions. Yes? So you can basically translate the bounds of on axions from supernova cooling to some bounds on this, and it turns out that the n equals 2 case, actually the strongest bound is coming from the cooling of supernovae, so it actually gives you, I think, more like m star is bigger than 100 TeV. Okay, so the n equals 2 is really not, and then you can have black hole production at the LHC. Yes, it's another topic that people have very have thought about carefully. Yes, I mean, if we are saying that the true Planck scale is m star, yes, once you actually reach m star, you should be able to form black holes, and then those will decay, and they will decay uniformly into all kinds of particles. So that's something that people have looked at, and so the LHC experiments are actually, whenever there's a new run, they are actually interpreting their data in terms of the absence of black hole production or the absence of the monophoton, monojet events into bounds on m star, and probably now m star is not 1 TeV but 3 TeV or something like that. All right, anyway, so that's the basic idea of large extra dimensions. Yes?
So how did you get this equation for R? Why is Planck entering that equation?
Yes, because you still have that relation that m Planck squared, yes, is equal to m star to the 2 plus n times the volume of the extra dimension, yes, and I just put here r to the n. I just assume that the volume of the extra dimension is roughly related to some linear dimension to the nth power. Yes? So now instead of, now what we say is that this is fixed, and this we just, declare to be 1 TeV, yes, and that's going to be now an equation for r. How large does r have to be to get 10 to the 19 GeV out of 1 TeV. Okay, so that's what the solution is.
And one more question.
Yes.
So what is actually the mechanism for localizing on the brain?
Right. So that's a good question. So that's we are not explaining that here. Yes. The claim is that string theory has objects like this, yes, that are localizing gauge fields. something that you understand is how to localize fermions. So that is something that you can understand just from solitons and four-dimensional theories. Yes. So when you have a kink, then at the location of the kink, fermions are localized. Gauge field localization is a little bit harder. Scalar is even more complicated. But here we are not trying to explain that.
But is something special going on that all the standard model is localized on one brane and only gravity is in the bulk? Or
yeah, absolutely. That's very special. Yes.
does it require a lot of tuning, model building? Is it easy?
I haven't really seen, a very complete model that fundamentally actually gives you this. So I presume it's certainly, I don't know any field theory version of that. Yes. Maybe the string model builders have achieved something similar to that, but again, that's something that that people usually don't address. Yes.
So once we set up the configuration of the brackets in flat, there's at least the configuration is stable under the resistance to reaction. There is no. It's in other words, once I set it up, they're not going to flat, they're not going to go away. They're to stay there. At least this setup because.
Well, again, that depends on the branes, on the stabilization mechanism. So you have to stabilize your radius. Yes. Do you need a stabilization? I guess yes, because you would get an exactly massless, radion, yes, and that will give you a fifth force, even if it's just 1/m Planck suppressed, yes. So you need a stabilization even for yes. It doesn't have to be super. It doesn't have to be a TeV or 100 GeV, yes, but at least should be an electron volt or something like that, yes. So that's all right. So I want to really move on to the main topic, which is warped extra dimensions, okay, because that's the one that will be most strongly related to the ideas that we were discussing yesterday. Yes. So this warped extra dimension will be a true solution to the hierarchy problem, rather than just being a reformulation like the large extra dimensional case. But it will turn out that it's a true solution, but it's not really a new solution, because it will be just a five-dimensional description, a five-dimensional version of the ideas that we have been discussing before. Okay. So in this case, warped extra dimensions. So we are going to consider a single extra dimension, unlike the large extra dimension case. Yes. So in large extra dimensions, one extra dimension is excluded. Yes. But for this one extra dimension is what we are going to be interested in. But the difference will be that the extra dimension will not be flat, but there will be curvature along the extra dimension. So there will be a non-trivial metric, background metric, which is called the five-dimensional Anti-Distiller space. Okay, so ADS5 metric. Okay. Now it may sound, daunting, is an Anti-Distiller, but it's really just saying that, well, the metric along the extra dimension is not flat. Yeah? So the metric is not given by just dx squared. Yes, but there will be some non-trivial factor here, r over z squared times beta mu nu minus dz squared. Okay, and so this prefactor here, yes, is the key. So this is what is called the warp factor. Yes. And this is again a consequence of the fact that this is a space-time with curvature. Okay, and what is really cool about it is that if you look at it at any point along the extra dimension, the four-dimensional space is flat. Yes, I mean our observed four-dimensional space is close to flat. So every four-dimensional slice here, yes, along the extra dimension is flat. Yes, because if I pick any particular value for z, yes, the induced metric is just going to be there's some constant prefactor once z is fixed, yes, but the four-dimensional slices are going to be flat, yes, and what will happen is that there's this warping that is happening as you go along the extra dimension. Okay, so this is the coordinate along the extra dimension, and in this warped extra-dimensional models, usually what happens is that space-time is ending on two branes. Okay, one of them is called the UV brane, and you will understand it in a moment why. And the other one is called the IR brane, or another notation of it is the Planck brane and the TV brane. Yes. So space-time is ending on these two branes. And this R here, yes, so this quantity is what is called the ADS curvature. This is telling you when you're actually going ahead and calculating what the curvature of the space is, yes, it's going to be related to this quantity R. Okay, so R is the ADS curvature. Okay. And if you are wondering where this solution is coming from, it's actually not very hard. Yes, if you take a space-time with a constant, negative cosmological constant, yes, this will be the solution to it. So if you take a negative cosmological constant, lambda less than 0, then you will find this ADS5 to be a solution. Yes, so this is actually a solution of the Einstein equations. Yes, with a negative cosmological constant, and then there are some funky things that you have to do in order to end the space-time on these two branes. Yes, I'm not going to go into detail about that. Basically, what you have to do is you have to put some particularly chosen and tuned tension both on the UV brane and on the IR brane in order to be able to get this space-time as the full solution where the space is ending on these two branes. Okay, so there is some tuning there, and it turns out so there is some tension here, V and minus V, and one of those tunings is just related to the usual cosmological constant problem. The other tuning is related to the fact that you don't want these two branes to attract each other or to repel each other. Yes, so you basically you want to make sure that this setup is stable. That will need this second tuning. What that means is that you're calculating this factor, this warp factor, yes. So this is something that is 1 around here, yes, and then the warp factor becomes very small over there, yes. It's just 1 over z squared, yes. That's what it is. Okay. Well, it means that the space-time doesn't necessarily have to be stable. Yes, if you don't pick the right value for the tension here, what will happen is that these two branes will actually fly apart or fly towards each other. Okay, so the space-time is just not there will be no solution with a that is static. Yes, these two will just attract each other or will repel each other. Yeah. Anyway. That has a relatively simple solution because you didn't add a radius stabilization here. If once you add radius stabilization, the second tuning you can do away with. Okay, you need a little more structure, yes, but that you can just stabilize the space-time, yes, and then you won't have this problem of having two tunings. There is just one, which is equivalent to the cosmological constant. So you didn't gain anything on the cosmological constant problem, of course, but you also didn't add any additional tuning there. Okay, so here is the key. Yes, so yes. Yeah, so this is the solution to the 5-dimensional Einstein equation. Yeah, so you take a 5-dimensional space-time, yes, and you add the 5-dimensional cosmological constant, yes. So 4 spatial plus 1 time direction. Yes, so this is an extra-dimensional model. Yes, so the way you think about it is that these 4-dimensional slices you think roughly as our 4 dimensions. Yes, and then there is one additional dimension that is orthogonal to it. Yes, and the nice thing here is that you get a solution where the 4 dimensions that you observe are flat. Yes, and the curvature is in the direction that is orthogonal to the 4 dimensions, yes. So that's something that is not in contradiction with our observations, yes, that our 4-dimensional space-time is roughly flat. Okay, so this is a really nice solution for that. Okay, so the most important thing about this model is that as you go along the extra dimension, the natural mass scales are actually going to change due to the presence of that warp factor. The 4-dimensional cosmological constant, if you tune this properly, is going to be 0. Okay? Naively, it looks like you have to tune 2 things to get 0 cosmological constant. So you think there's some, that you actually lost something. But what I claim is that if you add a little extra structure, which I won't have time to do, which is called the radius stabilization mechanism, yes, then actually you will get this almost 0 cosmological constant, yes, as it should be with just a single tuning. Okay, but it's, of course, it's very important. But you see that the effective cosmological constant must be 0, yes, because you look at all the 4-dimensional slices and they are flat, and they are supposedly a solution, yes. So you actually don't need to do any calculation. Once you believe me that this is a solution, yes, you don't actually need to do a calculation. It's good if you verify it by adding up all the all the tensions and all the curvatures and see what the effective cosmological constant is. But if you didn't get 0, then you made a mistake, yes, because you know that all the all the 4-dimensional sections are flat, yes. So the 4-dimensional effective theory has no other choice but to be flat, yes, which means there is no 4-dimensional cosmological constant. Okay, all right. Very good. So the most important aspect of these models is that the mass scales, the natural mass scales in this non-trivial background spacetime are actually going to be varying as you increase the extra-dimensional coordinate. The natural mass scale along the z direction is going to be given by r over z times the natural mass scale at the UV brane. Okay, so as you increase z, the natural mass scale is going to be warped down. Yes, so basically every scale as you move along this direction, yes, will be smaller and smaller and smaller. Okay, so now you understand why I call this the UV brane, the Planck brane, and why I call this the IR brane or the TV brane, because in the model that everybody likes to consider is a model where the mass scale, the natural mass scale here on this brane is roughly the Planck scale, yes, and then I go out far enough, yes, such that this r over z squared factor is 10 to the minus 16, and so the second brane there the space-time is ending is going to be corresponding to the TV scale. Okay, so that's the main idea here. So let's see one simple example, which is called the Rs1 model. Okay, so in this example, what I'm going to do is I'm going to put the Higgs, the standard model Higgs, on the IR brane. Okay, so it's exactly that setup, and put standard model Higgs on the IR brane. Rs1, of course, stands for Randall syndrome. Okay, so let's see how that action would look like. Yes, you have d4x times root g induced. Yes, I put it on the brane. Yes, so this is a 4-dimensional action, but evaluated on this non-trivial background metric. Yes, so it's a d4x, but when you put in the metric, you have to take that 5-dimensional metric and just take the 4-dimensional induced version of it. That is the one that is relevant on the IR brane. Yes, so I take this one and basically drop the you know, the extra dimensional components, because that's what it means that you project it onto the brane, yes. And then for Z, you take the particular location, which we usually call R prime, yes. That's usually the location of the IR brane. Okay, so you have the induced metric, and then you have your Higgs kinetic term, d nu h, and then you have to put here a metric, which is the induced metric again, yes, and then you put a potential here, minus lambda times h absolute value squared minus v squared over 2 squared, yes. You just take the usual Higgs action, yes, but put it in this non-trivial warped metric, yes. So now what happens is, yes, we are going to rewrite this warped metric just in terms of the four-dimensional metric, yes. So that will tell you that the Higgs field actually has to be rescaled. It doesn't have a canonical kinetic term, yes. So if I put in all of these induced metrics, yes, so I have d4x, I have the root g induced. What is the root g induced? Well, it's the root g that I calculate from a four-dimensional metric, yes, which has r over r prime squared times dx mu, whatever, dx mu, dx nu, eta mu nu, yes. So the non-trivial factor is going to come from here, so there will be an r over r prime to the power 4, yes. Is this clear where this r over r prime is? The root g, yes, so this is the determinant of the induced metric. Yes, the induced metric is this. The determinant of this would be r over r prime to the 8th power, and I take the square root of that, yes. And then the kinetic term d mu h, now I will rewrite it as eta mu nu, but then I will get now 2 powers of the inverse metric, yes. Sorry, 1 power of the inverse metric, yes, a g upper mu nu, yes, so that will give me an r prime over r squared, yes, and then nothing here. H squared minus v squared over 2 squared. Okay, so now this tells me that the kinetic term for the Higgs is not properly normalized, yes. So I have to rescale the Higgs field, yes. So I will rescale the Higgs field to get a canonically normalized Higgs, r over r prime times h, and then plug that back into the action, yes. What will I get? Yes, well, actually, once I do that, here I had 4 powers in the h to the 4. I had 4 powers, so that one is going to be completely properly rescaled, yes. But when I have the v, yes, that doesn't have the right powers of rescaling. So the final version of this action will be integral d4x times d mu h tilde squared minus lambda times h tilde squared minus v times r over r prime squared. Okay. So eventually the effect of this rescaling will be to give you the usual normalized Higgs action, the one that you are used to. What will actually be rescaled is this one massive parameter, yes, that you have put in, which is going to give you the Higgs wave. Yes. So what this is telling you is that if you thought you started out with, a very high, you put in, only very high values for the Higgs parameter, yes, the actual physical value that you are going to be observing is going to be rescaled by this power r over r prime. Yeah, so that's again an example of that whole rescaling that is telling you that the natural mass scales, as you move along the extra dimension, are going to be rescaled. Okay. Now, how?
Can you repeat the thing you said about the G induced?
Yes. So this is the induced metric. Yes. Yes. I take my 5-dimensional metric. Yes. And it has the full thing has an r over z squared in front. Yes. And it's a 5 by 5 metric. Yes. Now I'm asking, what is the relevant metric for this 4-dimensional slice? That's a 4-dimensional metric. Yes. The way you get it is basically you project this metric onto these 4 by 4 components, but this prefactor remains. Yes. So your induced metric is this prefactor times the normal Minkowski metric.
So this 4-dimensional metric would be at
Exactly, that's the four-dimensional metric, yes. On that brane, that's what you see, and that's what you need to use in order to construct your action there, yes. So I just did that explicitly. I wrote my Higgs action using this induced metric, yes. And what I find is that actually the one mass, the one parameter that was put in by hand that has mass dimensions, yes, after I canonically normalize the Higgs, yes, is going to be rescaled. Okay. So, I'm sorry? No, because so this is a 4x4 matrix, yes. So the determinant of the each component has an r over r prime squared. So the determinant is actually r over r prime to the 8th power, yes. But then there's it's root g, yes. It's root g, yes. It's the square root of r over r prime to the 8th. Yes? So that's how you get r over r prime to the 4th. And then this piece here, this beast, yes, is coming from the inverse metric, yes. Does it have okay, that's a good question. Absolutely, yes. So that's the next question, yes. So it's very nice that I was able to do that, but how about gravity? Is there still gravity? Yes. So let's get to that. Yes. So it's going to be, whatever your ADS curvature is, yes, and that's going to be scaled down by r over r prime. Yes? So it's basically going to be always the location of the brane. That's what will be the actual natural scale at that position. We'll get to that if I definitely want to get at least to the ADS CFT part. Okay, but first gravity, yes. So how about the Planck scale? Yes, how is the Planck scale related? So I told you roughly how the Wick scale is given here, yes, because it is going to be this warped down version, yes, because we discussed at the beginning the Wick scale is all determined by what that Higgs WAV parameter is, yes, and that's something that is going to be warped down. Okay, now how about the Planck scale? Yes, so there you go ahead and you start out with your 5-dimensional gravity action, yes, the usual thing, r to r prime dz, and here you have your d4x root g5 r5. Yes, so you just take your 5-dimensional Einstein-Hilbert action, except now you have to expand the metric not around the flat background, yes, but around this warp background. Okay, so you can do that. It's actually relatively simple to do. You will get a few of these warp factors showing up, and the relation that you are going to find is that m Planck squared, so that's the 4-dimensional one, is m star cubed times r times 1 minus r over r prime squared. Okay, so now this is really cool, yes, because what I told you is that the scale of particle physics, the scale of the Wick interactions, if I move it far out down in the IR, is going to be warped down. It's going to get this r over r prime factor. Yes, but the scale of gravity, yes, that is actually not going to be warped down. Yes, it has a very mild dependence on r prime. Yes, this term is you can almost forget about it. Yes, because there is a 1 minus this tiny term. Yes, so this one can naturally be large, yes. So you can take a theory where m star is of the order of 1 over r, is of the order of m Planck, yes, and your starting v is of the order of 1 over r, is of the order of m Planck, yes, and then r over r prime is of the order of 10 to the minus 16, yes, and then you will naturally get the scale of Wick interactions to be the TV scale, and the scale of gravitational interactions to be the Planck scale. Okay, so let me take a few minutes here just to talk to you about the ADS CFT correspondence. But for that, I need one more one more side remark, which is how does the Kk decomposition work in general for these warped spaces? Yes? It looks like I'm putting it in by hand, yes. The important thing is that the ratio, yes, is so the question is, where the, do I have to put, yes, so do I have to put this ratio 10 to the minus 16 in by hand, yes? Or is that something that you can actually relatively easily get from the theory with order 1 numbers, yes? So where does this come from? So that sort of is related to the question, like in the large extra dimensions, yes? How do I stabilize the radius? Yes? Can I stabilize the radius without putting in, very disparate scales into the theory, yes? And just start with a theory that has numbers of order m star. Okay. Now it turns out that actually, this r over r prime, yes, can be very easily stabilized at a very large value, or 10 to the minus 16, just by adding a scalar field in the bulk. Its mass is roughly of the order of m Planck, but maybe you can put in numbers that are 10 or 30 times bigger. Yes, you put in hierarchies of the order of 10. Yes, and basically you can get exponential. You can get those exponentiated. Okay, again, that's something that has a long literature. I know a lot about it, but I just don't have time to do it. Yes, is the radius stabilization. Yes, and that is indeed an additional required, ingredient to truly say that you have solved the hierarchy problem. Yes. Otherwise, exactly. But again, the claim is that it's actually very easy. You have to do exactly the kind of thing that I want to show you next, but I will only give you some very brief outline. You have to take a scalar field, so put a scalar in the bulk. In the bulk of Rs, yes. So that's not what we did with the Higgs, yes. We put the Higgs on the brane, yes, and just asked what its natural mass scale is. But here you put it in the bulk of Rs, yes, and just ask how does the Kk decomposition work now in the presence of this non-trivial background metric, yes. So you just go ahead and solve the 5-dimensional scalar equations of motion, except you have to keep these annoying root g factors. Of course, they are not so annoying because they are the ones that give you all the interesting new stuff. Minus root g m squared phi equals 0. So that's going to be the equation of motion. You do the usual thing, yes. So you write it as a Kk decomposition along the extra dimension. So there will be the 4-dimensional components, and then there will be the wave function along the extra dimension, 1 over root r, yes. Now these equations will be more complicated, yes. Previously they were basically just sines and cosines, e to the I n y, e to the minus I n y. Now these are going to be Bessel functions. Okay, so the key is that these will be Bessel functions. And the one thing I want to say about the Bessel functions is that, for large values, they are basically going to just be sines and cosines, but they are not just going to be Bessel functions, they will be z squared times Bessel functions. So the solutions will look like z squared times j alpha of mnz plus some one coefficient plus another coefficient times z squared y alpha mnz. Okay, so these are Bessel functions. For large arguments, they are just oscillating, but then you have these additional z squares here. Yes. So actually, they are going to be functions that are growing very strongly towards the IR. Yes. So the general Kk modes of these theories will be peaked in the IR, yes, except possibly a zero mode. Okay. So now why is this interesting? Why is this whole thing interesting? So this is the last topic that I'm going to steal another 5 minutes, which is the Adscft correspondence, because it's actually very simple and easy to understand. So it would be a pity to not do it. So the Adscft correspondence came originally from string theory, yes, and there it was noticed that a particular, string theory, type 2b string theory, in a particular limit was just supergravity compactified on AdS5 cross S5 was dual to a 4-dimensional supersymmetric gauge theory. And the important thing is that there's some sort of a conformal symmetry that is emerging from this anti-Distiller space. And the thing that I want to just emphasize is there is this conformal symmetry hiding. How can we see it already in this metric? Yes, so I have this metric R over z squared times dx squared minus dz squared. Yes, and I already told you roughly what is happening. As I move along the extra dimension, the mass scales are changing. Yes, why are they changing? Yes, let me move along the extra dimension. So do a scale transformation along the extra dimension. Yes, so I will increase z by a factor. Yes, so that tells me I had my extra dimension. I went from here to over here. Yes, what happens? Yes, well, the whole, there will be this 1 over e to the alpha showing up in the prefactor. Yes, and that can be compensated by doing the same scale transformation in the 4-dimensional coordinates. So this is compensated by x goes to x times e to the alpha. Yes. So what is the physics of this really simple? This is the heart of it. Yes, it's so as simple as this. It tells you that if I move from here to there, yes, that motion can be compensated by rescaling my 4-dimensional coordinates. Yes. So that tells you that the motion along the extra dimension from the 4-dimensional point of view is telling you that you are increasing your length scales, you're decreasing your mass scales. Yes, that's it. Yes, that's the heart of Adscft and all of these warped extra dimensions. You move along the extra dimension, yes, and the mass scales are going to be decreasing, just because there's this non-trivial background metric that you are doing here. Okay, so the motion along the extra dimension should be interpreted as a change in the 4-dimensional energy scale. Yes. Okay, so the 4-dimensional energy scales are going to be decreasing, just like you saw it with the Higgs, just like I showed you from the beginning. Okay, so this is what is called a holographic RGE. Yes, and so that's very nice. Yes, but then the question is, so that means that this whole thing is somehow corresponding to a conformal field theory. Yes, and that's what Maldacena did. Yes, and he saw that when you have the entire AdS5 space, you did get a true 4-dimensional conformal field theory. Yes? Now, in this Randall-Sandro model, you have something different, yes? Because you have these two branes where space is ending. Yes? So now that has important additional implications, yes? Because the fact that I have cut off the space here means that actually this conformal transformation, yes, is at some point broken hard. Yes? So the fact that I put in a UV brane, yes, should be interpreted as saying that the conformal symmetry has been broken, yes, and I just cut off the theory at a particular scale. So the location of the UV brane is just a lambda cutoff of the CFT. Okay. How about the IR brane? Now that is more subtle, yes, and that's why I wanted to make sure that I mentioned the Kk decomposition of the fields in this RS model, because what happens is that when I take the Kk decomposition, I will find all of these modes, yes, that are more and more peaked along the IR brane, yes, and those modes will have Kk masses that are roughly given by n over r prime. Yes? So how should I interpret that? Yes. So the best way to interpret that is that actually the IR brane is not an explicit breaking of conformality, but it corresponds to a spontaneous breaking of conformality. Yes. In the sense that in the sense that imagine that you had a theory that had a beta function that was very close to 0, but not quite 0. The most well-known one is QCD, yes, because the beta function of QCD is almost 0 when you go to very high energies. Why? Just because it's asymptotically free. Yes. So at high energies, QCD is an almost conformal theory. Yes. Then you go to lower and lower energies. Yes. You will start seeing that actually, there's a coupling that is growing. Yes. And at some point, the theory is going to confine. Yes. It gives you chiral symmetry breaking, and it gives you a lot of hadrons. Yes. So these Kk modes, yes, should be identified as the bound states that are present in the theory where, this almost conformal theory eventually became non-conformal, became confining, broke chiral symmetries or didn't break chiral symmetries depending on, what theory it exactly was. And these Kk modes, yes, will be the composite bound states of that CFT. Okay, so these are the bound states. Okay, so now if I put a Higgs on the IR brane, yes, I can think of that as a state, yes, that you don't actually have to exactly put it on the IR brane. You can put it in the bulk and just have it exponentially peaked. Yes, what does that tell you in the CFT picture? Yes, it's telling you that actually that Higgs, yes, is to be interpreted as a composite state. Yes, that is due to the strong dynamics becoming confining. So this is how you are going to connect this to the whole picture of composite Higgs and pseudo Goldstone boson Higgs. So I wish I had 15 more minutes because I could say a lot of other interesting things, but I think I really should finish now. I'm sorry? I think there is no discussion. Is there a discussion section? Okay, so if you guys want, I can talk for another 15-20 minutes in the afternoon and finish up this picture. It's not mandatory, you can go and play soccer or or you can go and play basketball with me afterwards.
You will play?
All right, let's finish here. Thank you.
Breaking is only in the CFT picture. In the ADS, you actually put in a brane.
In the ADS, you actually put in a brane, yes.
So it's not some kind of dynamical result. It's like you actually stabilize with that.
Well, I mean, you should stabilize the location of that brane, yes. Yeah. But at this point, you are just